So I made a very bad forecast. So this is not a lunch break. So I'm gonna use the last 1.5 hours, just like a 3 hour. So I have prepared another workshop for you for the safety inventory, but I think maybe we have to skip it for the sake of the time. But this is quite similar to our new spender problem, but you can derive in a different setting, another safety stock measure for the case of the continuously reviewing inventory model. So for those who are interested in, you can look for continuous review models, especially there's a famous policy made by R and Q. This R is reorder point, and Q is for the order quantity. So here, this policy works like that. So I have a continuously reviewing inventory, so I know when it's going to go where in a continuous time period. So because of that, I can set up a point which is called by the reorder point, and then whenever inventory touches this reorder point, I can make my order. If my order arrives immediately, then my inventory position would increase immediately. However, this is not always the case, and if I have some lead time, then my order here would make an impact here, but my inventory position at that time would not be the same as this reorder point. So it can be either positive or it can even go below 0 and make a back order. So this is just a similar problem that we had before in terms of the order point. So if we increase the reorder point, we have a small chances of having backorder. But if we decrease the reorder point, we essentially decrease the number of the inventory that we will have. So it's a trade-off between the two, and we gotta determine the best reorder point and also how many parts to order. This is actually quite complex problem because we need to take care of the two different parameters and we need to optimize it one by one. But in practice, most of those difficulties, we kind of fix this. And did you learn any order quantity in your production planning courses in your undergraduate? Q, what reminds you? 뭐 있어? Q. E, O, Q. That's the only order quantity that you have learned. So we are fixing this as EOQ, and then the problem remains to be fixing just only one parameter, which becomes much easier. Okay, so I tried to test your ability to implement this with another Excel file that I have given to you. It has some of the ROP and the safety stock relationship, which is not linear at all. So if you are interested, you can try implementing the missing numbers in the Excel table. Then you will find out an interesting relationship between the R and safety stocks. 테이블이 있나? Do we have table here? Probably not. 있지? So I'm skipping most of the part. By the way, why is it important? Because sometimes we need to calculate the expected shortage per replacement cycle, but this is nothing but your expected shortage. We actually have calculated this from our news vendor example because this is similar to expected D minus S positive part, right? So that's the shortage. So as long as we have expected shortage, we can divide it by Q, and then it will go to the fill rate. And fill rate is an important measure in practice. So you have a fill rate of 90%, meaning that if your order quantity is 100, 90 of them will satisfy your demand, okay? And there could be 10 additional demand that cannot be satisfied due to the shortage. So that's the expected shortage ratio. And you can calculate it from the Excel spreadsheet as usual from the similar calculation that you have done for the use vendor problem. So that's why I'm skipping it. So I'm very comfortable of skipping this part. Okay. Oh, there's so many slides. So I am skipping a lot of slides. Okay. So this is resulting fill rate and safety stock relationship. Actually, there's no fixed or simple function describing the relationship between the fill rate and safety stock. You actually have to carefully calculate this number based on the fill rate. And you know the fill rate because fill rate is coming from this formula. So you gotta have to calculate expected shortage. And since your order quantity, you can fix it. Actually, as long as you have the expected shortage, you can calculate the fill rate. However, in order to calculate this expected shortage, you need to have an idea about the safety stock because depending on the safety stock level, your shortage can change. So it's quite related in that way. And numerically, if you calculate this relationship altogether, you gotta find out that the safety inventory is increasing in an increasing manner. So basically like this. So from 99.5 to 99.6, you gotta have almost double up the safety stock. So as you increase a little bit more and more, you gotta have a lot of inventory. That's the typical trend of the inventory, safety stock inventory in practice or in theory. So that's why it's very hard to satisfy or cover all the area that of interest for you completely. So that's why companies like e-commerce companies in Korea is doing a great job because it covers from Seoul to Pohang, Busan, and everywhere within 1 day or 2 days. So covering completely means they are stocking a lot of stocks, a lot of products in their warehouses. So probably if you just to decrease this kind of coverage, complete coverage into 95%, probably you can reduce almost half of the inventory. So that's the typical number that you have for this inventory and safety stock. So I was thinking of a new workshop, but if I do that, I will finish my second hour just for doing this. So I just skip it and maybe instead of it, let me introduce the other problem, the last problem probably for this lecture, which is called by dual sourcing from multiple suppliers. So what is dual sourcing? Basically, you have more than 2 suppliers. Then those 2 suppliers may have some unique features. So I can say that one is expedited supplier, meaning that it has a higher speed and shorter lead time, but with increased unit cost. The other one is a regular supplier. The lead time is a bit higher, but the unit cost is a bit lower. So you have typical 2 different characteristics of the suppliers, and I want to know what is the best policy sourcing from those two different suppliers with a different lead time and different cost. So this is a bit complicated problem. This becomes especially more complicated if the lead time difference is strictly greater than or equal to 2. So why does it matter? So let's say that this is the simple case. Why is it the case? If this is 1, then if I order from this time to both regular and expedite supplier, and see what's happening. At some point of time, E, the expedite supplier's order would come first. And then right after that, regular supplier's order would come. So there is no order between those two periods coming in, which makes this problem a bit simpler because I can pack it as a 1 because there's no further orders coming between those two periods. If this is 2, there's a strange thing happen. So here, this is regular, this is expedite. Then I need to also consider another order that are ordered previously and coming into this time. So not only I need to consider 3 time periods here, but also I need to consider more than 2 time periods for the ordering time. And if it becomes larger than 2, then the window is always increasing. So window is not increasing on the arrival period, not just for that, but for the ordering time as well. So it actually double up the windows of our interest as the difference between the two lead time is getting increasing. Okay. But in practice, the lead time difference can be quite high because and we find that for the case of 1 time difference, we call it as a consecutive lead time. For the case of the more than 2, we call it as a non-consecutive lead times. And for the case of this, the optimal policy is already known. Okay. For the case of this, it's more complicated. So no policy type is known for this type of complicated case. That doesn't mean that we cannot do anything. Okay, we can still calculate numerically what to do. Or it is known that S, the lead time difference goes to infinity, or lead time basically, this goes to infinity, getting longer and longer, we got an asymptotic optimal result as well. So, which is still useful, not exact, but still useful because that can be my base policy. So what we have done is we want to prove that what happens for the non-consecutive case of 2 suppliers. We find that this looks quite complicated, periods between the arrivals of orders. So we have to think about the pipelines of the inventory, which means that we have to have a large dimension of the space to cover. Still, I want to emphasize that numerically, probably this is not easy, but still maybe doable in some ways. However, proving which type of policy is optimal is a different story, completely different story. The last topic, which is quite important but not investigated extensively so far, is a supply chain risk, obviously. Let me explain why this is so far so challenging to investigate. So supplier uncertainty is very important. We have seen many related news articles regarding suppliers uncertainty. Some parts are fails, or some in the logistics courses in the middle that you have some problems. So this can be a quite big problem. So sometimes you have a problem in the emblem of those car, and although all the other parts are quite normal, because you cannot use this Ford mark in front of the car, you cannot sell it for a month. And considering the cost of those emblem compared to the price of the whole car, you may say that please stock those emblems in your warehouses, as many as possible, right? But if you start thinking like that, you will end up with stocking all 20,000 number of parts in a car, which can cost easily $1 billion. Okay, so this is not an easy problem at all. So anyway, finding out the most critical parts for the part supply chain is an important problem, but we got some progress in finding out the best combination or portfolio of those parts in some sense. But what is still quite hard for us to see is not this one. So for example, if we have to assume some of the supplier uncertainty, meaning that some of this part supplier is not able to deliver the parts for 1 month or 2 months. What can happen? And what is the best amount of the inventory I have to prepare in order to mitigate this kind of event? That is not frequently occurring, but once it occurs, it can take up to 1 or 2 months, right? So this part of the theory is almost done here. So we can basically use discrete time Markov chain to model this a random disruption of the supplier. And if we can successfully capture this discrete time Markov chain in our supply chain or the inventory model, then we can apply the simple new spender model with the new Markov chain structure of the disruption. So here, instead of the customer random demand D in the new spender problem, now we consider a source of uncertainty not for the customer demand, but for the disruption of the supplier. So our demand, the customer demand is fixed by D here. It's always D. But the problem is in certain time periods, the supplier may work, but at some point of time, it may not work. Once it's not working, it may not working for several times. So this is captured by discrete time Markov chain, and then I can apply a corresponding inventory model that are quite similar to the new spender problem. So it turns out that by applying this kind of discrete time Markov chain structure, I can actually capture a quite similar function of Fn which actually depicts the steady state probability that the supplier in a disruption has lasted n periods. So here, f of n is not referring to the customer demand. This f of n refers to the number of periods that the supplier is in the downtime, is under disruption. So by using this function, surprisingly, we can say that our new cost function and optimizing it, my result would be the S, the optimal order quantity or the optimal level of the inventory that I have to take is just quite similar function of the F. It's not exactly the same, but surprisingly similar. So we still use the same f of inverse function, but here f of n has different meaning. But anyway, we are using f of inverse as the same as the Nussbender. So this is what we call by supply chain disruption and Nussbender case for the disruption. So I can apply the same theory, and the remaining challenge is how to calculate this f. Because right now I have modeled it with what? Discrete time Markov chain. So what do I need to know? I need to know basically the Markov chain means I know what? P, transition matrix. If I know the transition completely, it's quite similar of my knowledge of distribution function in the customer demand case, right? But I have only limited amount of data. Can we convert it into what? Data-driven disruption? You have another challenge when you try to convert this into data-driven manner. Why? If you want to convert your problem, customer demand into data-driven, you have a lot of data. For supply disruption, how many data do you have? For 99% of 99.9 amount of time, you got working, and only one not working. So this kind of the data is not that helpful for you to decide the actual transition, which actually occurs quite rarely. So you gotta have another idea and approaches in order to capture the data-driven disruption event, or you gotta have a lot of more data from other similar industries, similar part. So this is another challenge in the disruption field. So unfortunately, you don't have enough size of the data to make your transition model correctly. So this gets even worse when you think about a supplier uncertainty. Where is it? Like that. So think about semiconductor production shortage. How often have you observed this kind of semiconductor shortage in the automobile industry? As far as I know, first one. So it's very hard. Actually, I had a similar problem when I was working for a financial company, Bloomberg. I was actually working for a default probability model department. Okay, what I was doing is estimating the company's default probability. So what is the main data that I have access to? Company's default event. So I was looking at in 2008, the financial crisis, right? How many default did I see? It was around a couple of hundreds, 200, 300. That was the maximum number. On average, how many defaults do I have? Probably a couple of 10, 20, 30. So which is too small. But I have to identify the default probability based on thousands of companies for this limited amount of default events. So I had to figure out how to do that. And maybe you can apply similar knowledge. So the reason that I'm explaining this is probably sometimes you can borrow a good idea from different fields, different industries. So that's why you need to talk to many various friends outside of university, okay? So some of the ideas can come from finance field because obviously disruption is also quite of interest for the finance department. So I guess, can I do that? No. Okay. The next topic is, let's say that I have both demand uncertainty and the supplier uncertainty. Looks like this is quite practical problem, right? But that must be very messy problem. I don't know what to do. We don't have any known structure for those customer demand and the supplier uncertainty all together. So although it looks quite nice, this is quite challenging area. So we have no idea what kind of policy is working here. So if you can contribute a little bit of this, then you have a good chances to be very famous. If you have an idea, please come to me. Let's do it together. This was a huge Okay, I was using my time. So for the remaining time, we have some progresses in our multi-echelon supply chain as well. So maybe I can finish it within 5 minutes. Okay, so our supply chain is not a single company. It's a combination of many different companies either in a serial way, assembly, distribution, or tree, or any general form. So it's quite complicated, and it's getting worse because sometimes we don't know what the other company is doing. Even if we know the other company is doing exactly, that's still a challenging problem because you need to incorporate the other company's decision in your decision. Okay, so it's much more complicated one, and fortunately for this type of a system, and if you completely centralize the decision such that you know what the other part or company is doing exactly in real time. Then we have an idea of what to do. Okay. So the known result is for this kind of a different system, serious system, we can apply a notion of a echelon. So what's the echelon? This is the echelon. So let's say that this is customer demand, and we are going up to the supply chain. So this can be a manufacturer, this can be warehouse, this can be the retailer, and this can be the customer. So for all those serial chain, we can define an echelon. Echelon always comes from the company that are closest to the customer. So in this complex multiple companies inventory decision, it's good to aggregate all the inventory coming from 1 to J as echelon J, and the total inventory is controlled for the summation of the inventory of those companies. So echelon 1 is this company. Echelon 2 is 1 and 2. Echelon 3 is 1, 2, and 3, and so on. So it's increasing in the left-hand side. And then if we keep controlling echelon-based base stock, for example, I have a base stock for echelon J, base stock for echelon J minus 1, echelons for base stock for echelon 1, which would be the same as the company 1, right? So if I keep going in that way and increase my echelon 1 by 1, it is well known that this kind of the echelon-based base stock policy is optimal for this kind of system. But still, we only know the structure. And it remains to find out this S. This is not easy, right? Because we have multiples of the echelon-based stock. So for 1 to n, we gotta have 1 to n base stock level, which is much harder to calculate, right? At the same time. And to make it worse, your S1 decision will heavily affect your decision on S2, S3, and so on. So, which is very hard. But fortunately, we have a very nice theorem. So let me just show you the result. So this is a series of equations with 1, 2, 3, 4. And what they are doing is they found out that we don't actually have to do this optimization from S1 to Sn at this simultaneously. They actually found out that there is a way to do the optimization from S1 first, and then goes to S2, and then goes to S3. So they found that this problem can be separated one by one in a layer. So this is a very rare case. And this only works for this multi-echelon serial type supply chain. So this is very famous result. That's why in the textbook, we call this as a fundamental equation for supply chain theory. Because this makes this quite complex interrelated problem into a simple separated problem. Good. However, this does not look simple. So I know I can do one by one, but still, calculation of each of them is not easy because all the cost parameter, cost function is quite complex. And we are not just dealing with one cost function. We have to deal with 1, 2, 3, 4. So at least 3 different cost functions for each echelon, so which is quite hard to update and navigate. So because of that, I have a very nice idea to introduce to you. So the other approach that comes on next is, now, still this is a quite hard problem. So the remaining thing is how we can calculate these remaining parameters easily. I think this is the area where these engineers can contribute. So basically what they do is they just truncate the system into some part and then change the penalty cost and holding cost a little bit to make them equivalent. In other words, the echelon decision of S1 and Sj here and there are the same. And then they change the structure by making it simpler. So saying that I want to have this holding cost of all of the different stages as the same. If the holding cost of all stages are the same, then I don't have any incentive to hold an inventory into the upper division. It's best for me to push as much as possible to the lower division. So this will make the problem quite simple as one decision problem. So by fixing everything all together. So why is it great idea? Because right now I have H1 here holding cost, and the holding cost of HN is the smallest one. And I can just make it the same. And if I make it the same, then I can make the problem just like a one-dimension problem. Then what is a good candidate for my unified H? There could be a smallest possible one, largest possible one. So I can put 2 different values of H, I'm sorry. So the smallest one is the first one, H1 here, and the largest one would be summation of everything. So anyway, the details are not that important, but the idea is, let's say that I have the lower bound of holding cost, upper bound of holding cost. I can put it and make it unified the same. This will solve the upper bound problem and lower bound problem. And then my exact problem will be in the middle of the upper bound and lower bound problem. So they even make it simpler by calculating what? By calculating just lower and upper bound, and then half of it. Amazingly, this simple solution is almost perfect, 0.24% error. And the good thing about it is this is not a numerical result. This is formula. Formula to what? Similar to Newsbender problem. Okay? So what do we need? Still distribution. But if we know the distribution, we can simply obtain this result, which is close to the optimal echelon-based stuff. So what are the remaining things that we have to do? Probably, as we learned from our previous problems, extending this beyond this distribution assumption can be an interesting research topic, right? And that will probably need another techniques like bandits or DRL or anything else, or any types of the machine learning can help. Okay, so thank you for your attention. I just have skipped most of the part for the last session, but hope you find these kind of topics interesting and useful. So thank you so much. So for those who finished my homework, please come to me. Yeah, I can give you the prize. Where are we? Yeah, I have some books to read to you. Yes. Good work. Good work. 수고했습니다.
수고해주신 우리 박건수 교수님한테 다시 한번 박수 주시고. 네. 이것으로 2025 유니 펠로 윈터를 마치도록 하겠습니다. 예, 참여해주신 여러분, 다시 한번 감사드립니다. 감사합니다.